Everyday industries like pharmaceuticals, textiles, pesticides generate large amounts of micropollutants that find their way into our water streams. Regular water treatment processes cannot eliminate them. Their impact on health is of increasing concern. More stringent regulations will soon require new solutions to eradicate these micropollutants. Advanced oxidation technologies are uniquely positioned to address this challenge. They generate hydroxyl radicals, a species with a particularly high oxidation potential that are capable of destroying the most refractory organic molecules. In the frame of a project founded by the French National Agency for Research, ANR, Saint-Gobain, its academic partners, IEM Montpellier, LGC Toulouse, LGE Paris-Est, and the company Actibio have worked on an electrochemical advanced oxidation process. It consists in an electrochemical production of hydroxyl radicals thanks to a ceramic anode made of TiOx, an electrically conductive titanium suboxide. In this example, the anode is a porous titanium suboxide tube with a porosity of 30%, the average pore size being 1.5 to 2 micrometers. A pilot has been set up in order to test this type of electrodes. The microporous titanium suboxide tube is inserted into the module. It is connected to the positive pole of the generator and works as the anode of the system. In the cross-flow configuration presented here, the effluent to be treated is injected under a slight overpressure into the gap between the anode and the cathode. Because of this pressure, part of the effluent flows across the porous walls of the titanium suboxide tube. This is the permeate. For the permeate, the contact between the hydroxyl radicals produced on the surface of the anode and the molecules to be treated is optimized, leading to a very efficient degradation. The other part of the effluent does not cross the porous tube. This is the retentate, that is recirculated. We are going to test our device for AO7, a dye that is refractory to most regular treatments. A concentration of 175 milligrams per litre of AO7 is fed into the pilot tank. This corresponds to a total organic carbon content, referred to as TOC, of 77 milligrams per litre. Once the pump is on, the titanium suboxide tube is polarised. In this example, a current of 1 amp is applied. Of course, this needs to be adjusted depending on pollutant concentration and flow rate. We can note that the permeate is completely clear. Moreover, the TOC of the permeate is only 1 milligram per litre, which proves that our device was able to get an almost complete mineralization of the dye. When treating effluents with a high initial TOC, there is a risk of fouling the porous anode. To avoid this issue, other electrodes have been developed, like these titanium suboxide foams, with pore sizes of several hundreds of microns, or these meshes with an aperture that can reach several millimeters. These porous anodes can be used in a planar configuration. The effluent to be treated is circulated through a set of porous anodes and cathodes. On this example, a pharmaceutical effluent is recirculated through a lab cell with 2 cathodes and 1 anode. We observe a complete decoloration of the solution, which corresponds to the full mineralization of the pollutant. The TOC is close to 0 after the treatment. These devices have been successfully tested with many types of refractory organic pollutants. Saint-Gobain can tune the pore sizes to your specific application to optimize the degradation efficiency for a minimum energy, while avoiding the risk of fouling. If you want to learn more about this system and our capabilities, please contact us.